A sporting goods manufacturer designs a golf ball having a volume of 2.48 cubic inches. What is the radius of the golf ball? If the ball's volume can vary between 2.45 inches cubic inches, and 2.51 cubic inches, how can the radius vary? Use the epsilon delta definition of a limit to describe this situation. Okay, so we're talking about a limit, and we developed this definition of the limit that involved epsilons and deltas, allowing things to vary and then restricting some sort of x value. Turns out this does have applications in the real world through questions as such. Let's solve these one by one. Okay, so part A. I think what we need to recall is the volume of a sphere. Thanks, Archimedes. Indeed, Archimedes showed the volume of a sphere using his method of exhaustion. 2,500 years ago. He also used the lever that he invented. The volume of a sphere is equal to 4/3 pi r cubed, where r is the radius of the sphere. So we are given, what is the radius of the golf ball? Well, we are given that the volume is 2.48 cubic inches. So what we can do is grab that and plug it in right here and then solve for r. I don't know if you guys noticed I have this cool laser pointer now. I'm excited about it. So here's how we can do this. We're going to need a calculator. Oops, I wrote the same thing. Therefore, 2.48 cubic inches is equal to 4/3 pi r cubed. That tells us that r is equal to the cubed root. Well, I'll show more steps. That tells us 4 pi r squared, r cubed, is equal to 3 times 2.48 cubic inches, which of course tells us that r cubed is equal to 3 times 2.48 cubic inches divided by 4 pi. Cube rooting both sides of the equation, this tells us that r must be equal to the cubed root of 3 times 2.48 divided by 4 pi inches. Notice the inches escaped the cubed root. And that gives us our answer. Let's see. I wonder if there's some sort of, I feel like 2.48 is nicely divisible by 4. But I'll plug it into a calculator here. 2.48 times 3 is equal to 7.44 divided by 4 equals 1.86 divided by pi is equal to 0.59. Take the cubed root. That is 0.839. We'll round that up to 0.84. Almost a whole inch. And I guess that makes sense. I'm trying to imagine a golf ball right now. It feels like it's going to be a big golf ball, but that's okay. We can, of course, check by plugging that in to this equation right here and checking that the volume does approximately equal 2.48. All right, so now we have this new question. If the ball's volume can vary between 2.45 cubic inches and 2.51 cubic inches, how can the radius vary? Okay, so this is indeed an epsilon delta sort of idea. We are saying that the function is varying. So we have what the function should be right here, 2.48. The function should be that, but apparently we can lose 0.03 and we can let it vary that much, or we can add 0.03 to get to this upper bound. That minus 0.03 and the plus 0.03, that's our epsilon. We want to keep that in mind, especially once we answer this guy. And the limit, quote unquote, is this guy. That's what we want the volume to be. So this volume, the output of our function, can vary from here all the way up to this. But remember, our function really is this. This is the function for our volume. So let's see how that goes. We know, and I guess I can kind of do two birds, one stone. I kind of just answered part C. But we know that the volume must be bigger than, it says can vary between, so I'll use strict inequality, bigger than 2.45 cubic inches. I'm writing really small all of a sudden. Let me fix that. There we go. 4.5 cubic inches is less than our volume, which also is less than the upper end, which is 2.51 cubic inches. But easy peasy. We want to see how the radius can vary given those restrictions on the volume. So all we have to do is plug in our formula for the volume of a sphere. Remember our inequality rules. And then solve for r. So I can multiply through this entire equation by 3/4 times pi. The pi is in the denominator. 3 divided by 4 pi. And let's do that. (2.51 cubic inches). And of course, take cubed roots throughout the inequality. We can do that because everything is positive. And also, it's actually a cube. So even if it was, we don't care if it's positive, negative, or who cares. Cubed roots are very well behaved, well, at least more well behaved than even roots. So what we have is the cubed root, 3 divided by 4 pi, times 2.45 cubic inches, or since I have the cubed root here, I can sort of extract the inches without a cubed root. And we have the cubed root of 3 divided by 4 pi times 2.51 times inches, and both of these can be put into a calculator. I really hate using a calculator. I'm not a big fan, but I will do it for this video. 3 times 2.45 is equal to 7.35 divided by 4 divided by pi. Should be very close to what we had for the radius here. It should be just slightly below this number is what we should get. I actually maybe should have done less rounding. That might be awkward if we get exactly 0.84 or we round to 0.84. Oh, shoot, I lost my track. I think that might be what we're about to get. It is a little bit less. I shouldn't have rounded so much, though. In fact, this also does round to 0.84. I should have added more decimals here. Shoot. That's okay. We'll come back to it. Okay, so this is what I got. Hopefully you're following along. 0.8. I'll give 4 decimal places to be super clear. 863 inches is less than R. And that's going to be less than, R is less than, let's see this other side, 3 times 2.51 is equal to, divided by 4, divided by pi, take the cube root. On this side I got 0.8431 inches. Okay, so let me redo this one up here and see what this actually was. Here, I'll erase this and give a few more decimal places. This R, of course, should be smack dab in between these two guys. We were wondering how much we can let this R vary. This is the perfect R. In other words, this is sort of like the A. And this is the lower bound, this is the upper bound. Okay, let's see. I've got 3 times 2.48 divided by 4 divided by pi, taking a cube root. Okay, here we go. 8397. All right, is that smack dab in between these two guys? I think it sure is. 8431. Yep, I think we're good. This one seems farther away, which is kind of interesting. But so how do we interpret this in terms of an epsilon delta definition of the limit? I think we can even make a graph here. Use the epsilon definition. Use the epsilon definition of a limit to describe the situation. Here's what's going on. There are a few things that are happening. If we were talking about epsilon definitions and things like this, epsilon delta definitions, let's go down here. Maybe I can go up here so I can see the question. Yeah, that's better. So let's interpret this. I think this has, we kind of have this in mind. And we also have an epsilon in mind and a delta in mind. I think there is an analogous player for all of these pieces in this question. And let's go one by one. I think the limit, the analogous idea to the limit, so the limit right here is what the function should be. The function is, of course, the volume. That's what we'll get next. But the limit is what the function should be. That's going to be our 2.48 cubic inches. That's the ideal volume of this golf ball. A is associated with the perfect radius. Okay? So what is the radius of the golf ball? A is associated with what we discovered. Oops. Oh no, I'm grabbing stuff. That's not good. Come on now. Right here. So A is the 0.8397 inches. All right. And let's see what else we got. We need F. F of X is analogous to our V of R. The volume depends on the radius. I didn't write that right here, but indeed, volume is a function of radius. So we have 4/3 pi r cubed. All right, and then here's the other thing. Epsilon is associated with how much this volume is allowed to vary. So I think it's allowed to vary, and that's given to us right here. It's allowed to vary between 2.45 and 2.51. And let's notice that the limit L minus, one way we can do this is L minus some sort of epsilon is equal to the lower bound. The lower bound is this guy right here. Oh my gosh. 2.45 cubic inches. And L plus the epsilon is equal to this upper bound right here. 2.51 cubic inches. And that through that we are allowed to conclude oops, I'm going into my other question. That therefore, solving for epsilon here, all right, we know what the L is. L's right here, so you can plug this in right here. Solve for epsilon. What you get is epsilon, or just use it, or just think, is equal to 0.03 cubic inches. So that's how much we are allowed to vary. And last but not least, what's the delta player? This is where we really have to think. How much are we allowed to let R vary? I think R can vary stronger on the upper end, so we want to choose a minimum here. It's not necessarily the same delta. In fact, in this case, it's going to be different deltas. The difference from R, the ideal R, right here to here is going to be, I think, less, or excuse me. Is it less? That's weird. Hold on, let me think. Well, we can just calculate it. It must be less. I don't know. Than the difference between here and here. So we need two things. We need to calculate two deltas and take a minimum. That would work if we wanted one such delta. So we can do something like this. So what's the player for delta? We want to find the difference between this number and this number. Since this number is bigger, we can simply take this number and subtract off this number. So one possibility for delta is 0.8397 subtracted by 0.8363. All right, so I'll write that down. Oh, here, this is like one option for delta, minus 0.8363, and that is equal to 0.0034, and that is, we can name that maybe delta 1. And then let's see the difference on at the other end. The other thing I want to calculate is 0.8431 minus this 0.8397, and that's going to be the difference between these two guys. The ideal R, which is this one, This is like the A value, and this upper limit. So this is the upper limit since it's larger. I started with that one, and then I took off the ideal R. Let's see what this is. 0.8431 minus 0.8397. And they are, oh my gosh, they're the same. How is that possible? It's probably due to rounding. That's kind of cool, though. 0.0034. And that is our choice for delta. I don't need to call this delta 1. There's only one because of how we rounded. We always should also round down. I don't know if or we should round this one up and this one down because we don't want to accidentally allow R to escape. So we want to be a little bit careful. If we want to be more careful, we would maybe round this up to 0.8364 and then round this one down to 0.843, right? You don't want to accidentally create an R value that will allow the volume to be more than what you want it to be. So that's our sort of a first example, and we could even draw a picture and everything like this. But I'm gonna stick with it there because I have another example, kind of cool. We're going to talk about circuits and Ohm's law. So Ohm's law for electrical circuits, like the one shown above, states that V is equal to IR. This is what a circuit looks like. We have some sort of voltage source right here. The circuit moves around, the current, excuse me, that's what I is. I is the current, moves around in the counterclockwise direction. And there's, at the other side of the circuit, there is some sort of resistance. So let's see what's going on. Resistor. V is the constant voltage, I is the current in amperes, and R is the resistance in ohms. Ohm's law. Your firm, okay, we're hired at some place. Our firm has been asked to supply the resistors for a circuit in which V will be 120 volts and I is to be between, 5.0 or 5.1 amperes and 4.9 amperes, 5 plus or minus 0.1 amperes. In what interval does R have to live for I to be within 0.1 ampere of the value I initial equals 5? Okay, so immediately I'm seeing that this is my limit. This 0.1 is playing like an epsilon. In what interval is what that's playing is where can we allow our x values? There's some delta that we are in search of. And R is bounded by that delta interval. So that's what we're searching for right here. So for the beginning, let's see. I is sort of like our function, but this seems like V is a function of I and R. V is a constant, though. V is told to be, we are told that V is a constant. In particular, V will be 120 volts. So here's how I can begin this guy. Here's my solution. I think I know that V equals IR implies my function again, right here, the limit of my some sort of function is I equals 5. So I can get I by itself in this equation, telling me that I, the current, is the same thing as the voltage divided by the resistance, the resistor. That's huge. And I also know that we do not want to allow I to vary away from I initial by 0.1, okay? So we know what I initial is, and the 0.1 is our epsilon. In fact, I'm going to write that. What was the color I usually use for epsilon? I think I used yellow. All right. And we also know what I initial is. I could have just gone straight to that. So I cannot vary from 5 ohms. Oh, excuse me, amperes by more than 0.1 amperes. Oh, but that means that V over R minus 5 in absolute values is less than 0.1. But that tells me that negative 0.1 is less than V over R minus 5, which is then less than 0.1. And we can solve for V over R. The thing that we want by itself is given in the problem statement. In what interval does R have to live in for I to be within 0.1 amperes of the value I initial equals 5? Notice we are working backwards. We want to force this to happen, but at the beginning we're assuming that this is true and then asking, okay, if this is true, what must R be to cause this true situation that we already have? It's a little bit backwards. We want to make sure that really all these steps are reversible, and they always are. And, well, always is a strong word. You can always, of course, check that they are, that you can go from here to here. Like so far, if this is true, this is certainly true. If this is true, then this is certainly true. And if this is true, this is certainly true. So we can go both ways. Anyways, I'm yapping too much. Add 5 everywhere. That gives us 4.9 is less than V over R, which is less than 5.1. So that is where our current can live, but we want to know where R can live, and here's how we do that. Let's see. Well, we want R by itself, but it's in a denominator. So I think what I'm going to do is actually look at both of these separately. So let me grab this one first. V over R. Oh, also, I don't know if it's strict inequality or not. I think it is a strict inequality. V over R is less than 51. 5.1. I want R out of that denominator, so I'm going to multiply both sides by R, which is something we can do as long as R is not negative. And then divide both sides by 5.1. So we would have V divided by 5.1 is less than R. And let's see, how about this one right here? Let me box that. That's really important. We also would have, from this guy, we would have 4.9 is less than V over R. Multiply both sides by R. 4.9 is 4.9 R is less than V, which tells us that R must be less than V over 4.9. All right, so this gives us an upper bound for R, and this gives us a lower bound for R, and that gives us that V over 5.1 is less than R, and that's from this right here. And then we also have that R is less than V over 4.9. But we are given this voltage right here. We are given this voltage that is given to be 120 volts. So this is an ohm. And that would be volts divided by amperes. It's less than R, which is less than 120 divided by 4.9 ohms. And okay, so we have decimals here. So let's go with, this tells us 23.5294, and that keeps going. Ohms is less than R, which is less than 24.4898. That keeps going ohms. And I wanted to say, if we want this to work and we don't want to get fired, we want to push this number upwards. So we want to make sure we're not ever rounding down here. We want to make how much R can vary more strict. That way we can meet the current more accurately, the current of 5 amperes more accurately. So what we're going to do is round down and say that we get round up on this left-hand side, 23.53, 24.49. Oh, see, I did the wrong thing. We want to round down on this side and up on this side. So I don't want 49. I want 48. There you go. All right. This is how we can, this is our leeway. This is our wiggle room for the resistor.